start. Yeah. So
Give me a moment.
Okay.
Well, is this maybe on your or on mine?
This is my stuff. Yeah. It's okay now.
Okay, good. Yeah. You can, so to speak. I mean, just tell me a little bit of what you have wrote.
Yeah. So yeah, G is GL and R, and K is ON, maximum complex subgroup of G. So there is the definition of admissible. So the representation of G on Hilbert space V is admissible if restricted representation is unitary, and each irreducible unitary representation of K occurs in it with finite multiplicity. So I think that means like this, V can be expressed like this, and EI is finite.
Strictly speaking, I think it's a little bit more complicated, and just a little bit more, because the restriction of this representation to K is maybe not strictly speaking a direct sum.
Yeah, but
it's a so-called Hilbert direct sum. Like, I mean, let me give you an example, and what I will do is I'm going to upload your note into my app here, right? And then I can add some comments. Okay. So, for instance, I'm just writing into your so for instance, I mean, here's an example. We take okay, it's a little bit, it's not an example which matches exactly this setting here, but it is just, I mean, we take as our group G, we take the compact group S1, right, which is basically the same as SO2, I mean the circle group, right, and we let this act on in fact on the L2 space of S1 by the usual action. So some theta f of and we think maybe for simplicity we think of S1 as R modulo C, right, and then theta f of t is just f of t plus theta. Now, what is the L2 space of S1? Well, it is the so-called Hilbert direct sum of this is just a symbol, but it's the Hilbert direct sum of e to the 2 pi I n t, which means simply that every L2 function has a Fourier expansion, right? So it just means that every element f of t can be written as an infinite sum. It's actually, I mean, it is not everywhere convergent. It's sort of, it's right. I mean, an L2 function is not literally a function. It's only defined up to a set of measure 0 or something. So I don't want to get into those but I mean, morally, I mean, it is I mean, we can express it in this way. Yeah, and then it is not really true that every that the whole representation is literally a direct sum. So I mean, with a condition that the square of those ANs that the squares converge, that the squares of the absolute values converge. So, but I think what one can say is probably that the following, the meaning of this is that V is equal. So given an irreducible unitary representation W of K, we can write V as a direct sum maybe I call this V1 instead of V prime, where V1 is in V is a closed K invariant subspace, and the representation W does not occur in V1. So let me just write, that it is impossible to embed W into V1 as a K representation. So otherwise it could be that there is another copy of W in V1, and then there is another copy and another copy, and then you have infinitely many copies. So the point is here that we can split off. We can indeed write V as a direct sum, but we take any of those irreducible representations, and then we write V as a direct sum of a finite number of copies, as a direct sum of a finite number of copies of W, and some other space. And in the other space, there's no, we cannot embed W into this other space as a G representation. I think this we can. One still would have to make it very. One can try to take this as a definition, and see. It's just sort of. For instance, in this example here that I just gave you, this would definitely be an admissible representation of this group, of this compact group on this vector space, and every representation every representation of S1 is indeed, it's just a power of the identity map, so to speak, which is the same as saying it is just this character e to the 2 pi I n t. But the whole vector, this Hilbert space S2 is not the direct sum. Otherwise it would have a countable basis as a vector space in the sense of linear algebra. But it doesn't have a countable basis. It has a countable Hilbert basis, but not strictly speaking a basis. It's probably not easy to write down explicit. Well, I guess, yeah, you can. Right? It is clear that. That this space, that in this example, maybe again I'll write it down here. So L1 of maybe I'll write R mod Z. It strictly contains the infinite direct sum of C times e to the 2 pi. Here. And why does it strictly contain this direct sum? Just because there are L1 functions which have infinitely many non-zero Fourier coefficients. Just take any sequence of ANs for which the L2 norm converges. And this gives you a function, but this function is not going to be in the subspace which is algebraically spanned by these characters, e to the 2 pi I n t, because any function in here is a finite linear combination. Yeah. So I mean here, for instance, a function which is not in there is the function from n equal 1 over n t.
Mhm.
This is indeed L2 function.
Okay.
But it's not a finite linear combination. But morally, I mean, the idea behind this is indeed that that it's, so to speak, the direct sum of irreducibles with finite multiplicities.
Okay.
But because Hilbert spaces are not, I mean, don't have, I mean, a Hilbert space which has a really a countable basis in the sense of linear algebra. And when I say in the sense of linear algebra, I mean sometimes people in functional analysis call what's called a Hilbert basis also a basis. So for instance, these infinitely many elements here, these e to the 2 pi I n t, are, some people would call this a Hilbert basis, meaning that every element can be uniquely written as an infinite linear combination, an infinite convergent linear combination. But then this is not called a basis in linear algebra, because in linear algebra, for it to be a basis, it means that every element can be written in a unique way as a finite linear combination. So and I think any Hilbert space which has a countable basis is finite dimensional. Otherwise it must have immediately infinitely many. I mean, uncountably many. That it's in some sense of uncountable dimension. But that's I don't have a proof for this. But I think that is probably.
And Hilbert space can be a real vector space or complex vector space, right?
We always, I mean, in what we are doing here, not in p-adic representation theory, but here we take all vector spaces to be complex vector spaces. We could take them to be real vector spaces in general. When people talk about Hilbert spaces or Fréchet spaces or other topological vector spaces, it can be sometimes over the real numbers or over the complex numbers. But for us, this simplifies matters a lot if we just work with complex vector spaces.
Okay.
So all vector spaces here in this paper are complex vector spaces.
Okay. So I think the definition of the admissible is redefined by Peter By theorem. So this theorem is from the Knapp's book.
So I mean, so the point is here what is meant by orthogonal sum. So orthogonal sum is not literally the sum in the sense of linear algebra. But it's a little bit, it's sort of a concept from functional analysis. This is sort of in the sense of functional analysis. But so philosophically, it is the right thing to think of it as being a direct sum, but it's a little bit more complicated. Unless it's a finite dimensional vector space, then that's literally true.
Also known as sum.
Yeah, then it's just the orthogonal sum of finite dimensional vector space. Okay.
So, and that low is admissible representation, we call a vector V is K finite if low K V spans a finite dimensional vector space.
Right.
So
yeah. So for instance, in the example that we had above, So G is equal to K is equal to R modulo Z, and V is just L2 of R modulo Z with a so-called translation action.
Translation.
What would be, what are examples of K finite vectors? In which case these are G finite vectors. Which functions have the property that when you let the group act on them, you stay within a finite dimensional vector space?
Yes. Finite sum?
Yeah. Finite sum of what?
A n e to the
e to the 2 pi I n t, right?
Yeah.
So if we let fn of t just to be this function e to the 2 pi I n t, then we see that theta fn of t, well, by definition it's fn of t plus theta. And you see this is 2 pi I n theta multiplied with fn of t, just because. So this is in the same vector space spanned by fn.
Yes.
Yeah. So every of those functions fn is a so-called eigenfunction.
Eigenfunction.
Yeah. It's an eigenvector for every group element. It's an eigenvector for every group element, and the eigenvalue for the group element theta, the eigenvalue is exactly e to the 2 pi I n theta. Yeah. So in this example, this is really a good example. I don't want to praise myself, but it's a good example. Each fn is an eigenvector for all theta in G, which is the same as K in this case. And therefore, each subspace generated by any of those is G stable. And therefore every fn, every function fn is a K finite function. In this case, K is a K finite function. And give me one more moment. Is a K finite function. And then every finite linear combination of these fn's is of course also a K finite function. Yeah, and any finite linear combination. And by the way, can be any element in Z.
Yes.
Is a finite linear combination of the fn's, and from this it is actually not hard to see that in fact every K finite vector is a finite linear combination of those. It's maybe not, but I think it shouldn't be that difficult to show this. So I think that's a fact with regard to this example that indeed so L2 R mod Z and then K finite. This is denote the space of K finite. Okay,
sub K.
we denote by subscript K.
Yeah.
This is indeed this direct sum, this countable direct sum.
Fn.
Which is span.
Yeah.
It's the algebraic span of the Fn's. And this is, by the way, also, a standard technique in the representational theory of real reductive groups to pass to this subspace of K finite vectors, because it has a nicer algebraic structure. So, some people like to look at the Hilbert space representations, and other people like to look at just sort of more from an algebraic point of view at these spaces of K finite vectors. And the best thing is to sort of to look at both aspects. Okay, so is every function is a K finite function, any finite linear combination? Yeah. Okay, and then C, right, and then we have the C infinity vectors. Right.
Yeah, if the map G to V, G maps to low GV is of class C infinity.
Okay. Yeah. In this case, in this example, every K finite vector is also C infinity. And that is true in general by the next proposition.
Proposition from Knapp's.
Right.
Yeah, K finite vector is C infinity vector, and Vk is stable under low bound
of the Lie algebra.
Yeah, Lie algebra.
Right.
Yeah.
Because every K finite vector is C infinity, we have also then, by its very nature of being a C infinity vector, a derived action, right? So if we, you don't, actually you have those formulas already. Yeah, this is the formula how, here. Here you have the formula how an element of the Lie algebra acts on a vector, and this is true for any. This is the formula which gives the action.
Yes. Right.
For any. Right. And then you go.
Yeah, GK module.
Right. Okay.
So GK module is vector space V that is both a Lie algebra representation of frac G and a group representation of K, satisfying these three conditions. But the first and third condition is trivially okay if we consider the corresponding representation. Yeah, right. So, and Vk is satisfy the second condition. So low Vk is GK module.
Right.
Yeah.
Yes. Okay. Yeah.
Okay. Then by Harish Chandra, there is bijection between closed G invariant subspaces U of V and the GK invariant subspaces UK of BK.
Right.
Mapping is like this.
Yeah. So again, in this example that we had before, V would be L2 of mod Z, and then VK is the direct sum of these Fn's, and somehow from a purely algebraic point of view, this is a nicer space to work with. And from an analytic point of view, this is maybe nicer. It's it's a complete vector space. This is just an algebraic vector space. But what is interesting is that that the G invariant subspaces correspond to the G invariant subspaces in here. So in this case, of course, we have very many G invariant subspaces because G is K in this example. But interesting.
So from this bijection, so in particular, low V is irreducible if and only if low Vk is irreducible.
Yeah. So this is then extremely useful. That this, exactly this statement here.
But in the paper, the Knapp says rho VK is algebraically irreducible, but algebraically irreducible. But I don't know exactly algebraically irreducible.
This just means
Just irreducible.
just irreducible.
Yeah.
Whereas actually, I mean here, when one should be a little bit careful, perhaps. I mean, this should really be topologically irreducible. Meaning that a representation is topologically irreducible if the only closed G invariant subspaces are the whole space and the zero subspace. I mean, it is certainly the case, even though these spaces are not very interesting, that for also in here in this example, there are very many subspaces in here which are G invariant but which are not closed. But I mean, they do not correspond to G invariant subspaces here, and they are not really interesting. But as a purely I mean, if one just says a representation is irreducible if the only G invariant subspaces are the zero space and the whole space, then it is not true that this representation would be. I mean, in this case anyway. But I mean, then typically, basically, all interesting topologically irreducible representations are not irreducible in the purely algebraic sense. I mean, usually, you can usually construct lots of non-closed subspaces by taking any non-zero vector in your vector space, and then you take the span. You let each group element act on this vector, and then you take the span of all these elements. And this is then, by its very definition, it is an invariant subspace, but it's basically never closed. So it's easy to find lots of subspaces which are G invariant, but they are then not closed. But again, those non-closed subspaces we are not interested in. They are somewhat pathological.
The right representation is irreducible, meaning is the restricted to K, VK, and rho bar VK are irreducible, right?
What is rho bar?
I wrote before, rho bar is corresponding representation to Lie algebra.
Oh.
Yeah. Just I denote rho bar.
Oh, I see. I mean, when we say that the Harish-Chandra module is irreducible, so you are asking, is it correct that saying that this is irreducible means irreducible?
Yeah.
Actually, no. For a very easy reason. I mean, because if you say it this way, at least if you write it down this way, it means this is irreducible, and independently this is irreducible, right? This as a representation of K, and this as a representation of the Lie algebra.
Yes.
Right, but you know already that this VK is typically an infinite direct sum of irreducible representations. So as a representation of K of the group K itself, this is almost never irreducible. And this is also most of the time. I mean, this could be irreducible, but it could also not be irreducible. So, well, what is meant when we say this GK module is irreducible? We mean as a GK module. So there is no subspace other than the zero space and the whole space, which is stable under the action of the Lie algebra and under the action of K. So So here, I mean, let me then correct
Yeah.
this. So I mean, this means this means no no subspace
invariant subs
other than 0 and vk is stable under K and the Lie algebra.
I'm confused. What's the difference from what you wrote and I wrote? So
I mean, it seems what you wrote, I mean, is saying that when one considers the representation. I mean, when I say no subspace other than 0 is stable under, I mean, it's stable under G and K, whereas you're saying no subspace, I mean, there is no subspace that is stable, no non-zero subspace other than VK stable under K, and no non-zero. You see, I mean, so think of those, I mean, for the moment, just pretend the action of the Lie algebra would actually be an action of another group. So we have two groups acting, right? Then what I say, what would be the right definition of the irreducibility of a Hara-Chandra module in this hypothetical context would mean there's no subspace on which both of those groups act. And whereas you are saying there's no subspace on which this group acts, and there's no subspace on which this group acts. But you see, I mean, you could have a subspace which is not the whole space and not the zero space on which K acts, and you could have a subspace which is not the zero space and the whole space on which, say, another group H acts. But this subspace is not the same as the other subspace. Right? I mean, you could have subspaces for both, but they are not simultaneously a subspace. Yeah. It's somehow the K action. It gives us a nice decomposition into irreducibles with finite multiplicities, and then the action of the Lie algebra. It moves these different irreducible pieces around. This is not quite correct because it does not really move. It does not map. I mean, the action of a Lie algebra element, it will not map a whole subspace, a K subrepresentation into a K subrepresentation in general. But it's actually, I mean, right. But somehow. I mean, there might be a subspace which is stable under the whole action of the Lie algebra, but that is then not a direct sum of subspaces that are stable under the action of K. Or you may have subspaces which are stable under the action of K, but they are not stable under the action of the Lie algebra. So the group K, the maximal compact K, and the Lie algebra together, they are not a group, but they give you, I mean, that's the whole point. They give you as much information as the action of the non-compact group G. So typically G, you should be thinking of a non-compact group. I mean, otherwise K would be equal to G. If G is compact, then K is G at least. I mean, I don't have. Maybe we'll find the time to look at a more interesting example. I mean, of course, the key examples to understand, for instance, are SL2R or GL2R, and we are going to get to this.
Okay.
And
then two other miscible representations are infinitesimally equivalent if their underlying GK modules are isomorphic. Right.
I mean, it is true. So it is true that if you have a single representation on a Hilbert space, then we can test whether it is irreducible by testing if the corresponding Hara-Chandra module, if the corresponding GK module is irreducible.
Mm-hmm.
But what is not true in general is that we have really an equivalence of categories, meaning, I think it goes quite a long way, but it's not clear, this is why we say infinitesimal equivalent.
Mm-hmm.
You may have two different representations,
Mm-hmm.
and you have isomorphic Hara-Chandra modules,
Mm-hmm.
but the representations are not isomorphic.
Mm-hmm.
Yeah. In some sense, this has to do with the fact that the representations are on Hilbert spaces or even on more general topological spaces. But I think here maybe Knapp only considers Hilbert spaces, which is okay. But you can still have sort of two a little bit different Hilbert spaces which give you the same, which give you isomorphic GK modules.
Mm-hmm.
If you look at a GK, if you look at a representation and then its GK module, the representation is sometimes called the globalization of the GK module. And you can have different globalizations, non-isomorphic globalizations of one and the same GK module. And people have sort of understand quite a lot about what kind of globalizations can occur and how far from unique a globalization is. But most of the problems in representation theory have been reduced to studying Hara-Chandra modules. So, but in fact, there is a famous problem, and this is sort of one of the key problems, but we are not going to touch any of this, is given an irreducible GK module, is there actually a representation of G on a Hilbert space which has this GK module? Right? So this is in fact, this is so to speak the problem in it's still one of the open, even though I think there has been lots of progress, but this book is just one book, but
by Knapp.
Yeah, it's also by Knapp and by Vaughan. Yeah, one also knows, there's also the concept of a unitary GK module, which is, so to speak, a GK module with an inner product. And finding out when and these are exactly the GK modules which come from Hilbert space representations, from unitary, so-called unitary representations, so which mean that the whole group G acts by automorphisms which are norm preserving. Yeah. In the very beginning, when you defined admissible, you cannot move this. Well, actually, you can. I see. Right. You're not assuming that. The representation of G is on a Hilbert space, but here you are not assuming that G acts unitary. You are just assuming that the restriction.
Yes.
So what people are very much interested in is now understanding those representations where actually G acts unitary, and then one starts by classifying all GK modules, and then one tries to answer the question which of those GK modules are unitary, meaning which come from a unitary representation, from a Hilbert space representation of the whole group G, and this problem is partly addressed in here. So in this book, there's some such theme. It's called inner product. Such a bilinear form, which is equivalent to having yeah, that the Harshanda module comes from a Hilbert space. So yeah. Okay. So, but for us, I mean, understanding which representations are infinitesimal equivalent is basically good enough for most of the problem.
Okay. And the remark from just Wikipedia. So if V is Hilbert space, then by Reed's representation theorem or metric coefficients have the form like this. For some two vectors. And then the corollary is from the Knapp's book. So infinitesimally equivalent admissible representations have the same set of k-finite metric coefficients. And then let's start the calculation. SCL plus minus MR is just with determinant plus minus 1. Then consider certain irreducible representations for M is 1 and 2, and for M is 1 the set is just plus minus 1. So irreducibility implies the dimension of V is 1, I think. So there are only two representations, one and sine, trivial one and non-trivial one. And for M is 2, the Knapp says he just interested in the discrete series DL. So there's a remark from Wikipedia. So if G is unimodular, an irreducible unitary representation is discrete if and only if one and hence all metric coefficient with non-zero vectors is square integrable on G with respect to Hahn measure.
Yeah, I mean, one can also take this as a definition by saying a discrete series is just another word for L2 or square integrable, and square integrable means that all these matrix coefficients are square integrable. So yeah, so this is yeah.
So, and there is construction for discrete series DL plus of SL2R from Knapp's book. So the Hilbert space for DL plus is VL, and F is analytic for image G is large than 0 and such like this. The known square is finite, and the action DL plus ABCDFG is like this. So we can define DL as induced representation of DL plus, and the Knapp says this is also irreducible unitary and square integrable. And I guess SR2 plus minus 2R is unimodular. I don't know exactly. So I think by the remark before, so DL is discrete representation also.
I think that's, I mean, it is true that SL2 plus minus R is unimodular. This is true, but this is not really, I mean, are you then, I mean, this is not really the reason why DL is a discrete series representation. Because there are other representations that are not discrete series. There are representations that are not discrete series representations. For instance, so-called principal series representations. So I have my so no, I mean there are other. So, but I think the second question is yes. I think these are. There are also the so-called complementary. No, wait. I mean, yeah, there are also the complementary series. So I think they are the most important ones. There may be just a few, very few ones that are missing. I would have to check. But that's easy to find out. There's another. So I think I mean here. Here, yes, but no, I mean here there are also in fact there are many irreducible representations which are not discrete series. So think about it for a moment. So this is actually right. Okay. So I mean, this is just a fact. This is not. But let's look at a different paper by. Actually, maybe also by Knapp. In the Corvallis proceedings. What was it? 1, 2, 3, 4. Yeah. Okay, so here it's first the discussion. Okay, so finite dimensional representations of SL2R or of this SL2R plus minus are never discrete series. And then there are the unitary representations. And among the unitary representations, there are the discrete series, as before. And then there are the principal series. And yeah, I think that these are all. I think the principal series representations, or the so-called complementary series here, or the other ones, they are not. They are all not. Discrete series. I mean, have a look. We do have to finish. I mean, stop in about 8 minutes or so. But did you? think there only these the ends are indeed discrete series. Yeah. So I mean, I don't really also here Wikipedia doesn't quite have a statement. If you find this book, I don't know how good it is. As a student I looked a little bit into it by search Lang SL2R. I don't know if you find an electronic copy or if you want to look at in the library. There might also be a discussion of the representation theory of SL2R in this book by Lang. I don't have this book here. I actually have a copy, but it's still in Germany. Yeah. Okay. Let's continue. So yeah. I mean, the answer is yes and right.
Yeah. This is the third question. So. Yeah.
The building blocks. Why? I mean, so you're asking why are those, so to speak, those building blocks, right? Yeah. This is somehow, and this I mean, this is in fact sort of the key result. And okay, I mean, he just, yeah. I mean, this is. Yeah, he doesn't explain that.
Yeah.
I see. Yeah. It's probably it would take too long to, I mean, to really work this out. Yeah. I mean, we can take this, so to speak, as a I mean, as a fact, as a matter of fact, it's sort of. I mean, there's the general philosophy that one that a representation of a group like GLNR, one tries to build them up from representations of smaller GLNRs, from so-called Levi subgroups. So from a group of the form. Right, so I mean here here we have GLN N1, and then we have here GLN2 and so on, GLNR, and then we put something, we make out of this group of block diagonal matrices, we make an upper triangular subgroup, a kind of a block upper triangular subgroup, by putting something up here, any entries, and zero entries here, and then this is called a parabolic subgroup, a standard parabolic subgroup, and then one can use these representations of these smaller GLNs. Yeah. And it is a key feature of groups like GLNR and SLNR that one can actually then that somehow, for instance, I mean, if you look at representations of GL, I mean there could, for instance, if we go to say SL3 or SL3 plus minus or GL3. So I mean there are some representations which come by what's called parabolic induction from those groups, from those smaller parabolic subgroups, And if n is 3, I mean, what are the parabolic subgroups, the standard parabolic subgroups? Well, it is this, which has a 1 by 1, a 1 by 1, and a 1 by 1, the so-called Borel. It is the one which has here a 2 by 2 and a 1 by 1 block. And it is the 1
by 2.
A 1 and then a 2 by 2 block.
2 by 2, yeah.
And then it is the whole group, so to speak. Here is the 3 by 3 block. And so what happens in p-adic representation theory, that there are some irreducible representations which are not subquotients. I mean, so if you then take an irreducible representation of this group and an irreducible representation, say, of this group, and you take the tensor product of those two representations, then you get a representation of the product group, which you can then extend to a representation of this group by making these so-called unipotent matrices act trivially as identity. And then you can produce a representation of the whole group G by induction. Okay. And then it may happen, sort of generically, that actually if you pick randomly an irreducible representation of these factors on the diagonal, and then you induce, you are lucky, in fact, and you're getting an irreducible representation. But sometimes you are not getting an irreducible representation in this way. And but then you can still look, I mean, then one can prove that this is still a representation of finite length, and one can look at the subquotients. Okay, so but then it could happen that if you use this process, so you take here an irreducible representation here, then you do induction, or first you do what's called inflation, and then you do induction, and then you take irreducible subquotients. You do the same thing here, and you do the same thing here. It could be that you're still not getting all irreducible representations, because it could be that there are some representations, well, you cannot just produce them by induction from these kinds of groups. And this is exactly what happens in the p-adic world. But there is a reason, and I cannot give you a very easy answer for this. I mean, there is, it has something to do, or I think people knew it beforehand, but it has then proved differently by Kesselman. It's sometimes called the Kesselman subquotient theorem, which has then proved also by other people, Bernstein and Gelfand. And one can, yeah, I do have an idea why it's true, but it's not sort of, I mean, it would go probably beyond. At least you don't have to explain it.
Okay.
But the beautiful thing is somehow for representation for groups like GL and R, there are no other. I mean, you don't need to go to if you take all these representations, the irreducible ones that come by this process from here and from here and from here, you get all irreducible ones. And that means, for instance, then when you look at GL4, oh yeah, okay, we have to stop here.
Yeah.